Nash Equilibrium concepts that we use for simultaneous games. Okay, so we're going to look at how to analyze sequential games as simultaneous games, and we're going to look at how to analyze simultaneous games as sequential games. Okay, so there's those two kind of dual ways of thinking about strategic interaction. Simultaneous games where you can't communicate with one another, you can't observe what the other people are going to do, but you can think about it, and you have the payoff matrices. And you've got the sequential games where there's kind of an order of play, and people get to observe what other people can do, and they make their moves accordingly, and other people can anticipate that and also make their moves accordingly. But those two ideas will fit together in quite a neat sort of way. And then we're going to turn our attention to games with imperfect information. Okay? So far we've been really talking about games with perfect information where everybody knows everything they need to know about players in the game, what they can do, what information everybody has. There's no real uncertainty. Okay? But we're going to see that, more interesting games are where there is an element of uncertainty. So tomorrow we'll do a little card game, and I'll talk a little bit about the concept of uncertainty and tell you how I think about uncertainty by looking at how the sports betting bookies at the TAB set their odds. Okay, so we'll do a little bit of thinking about, we won't actually do any betting, but we'll look at how they might set their odds and think of it as a way of representing your uncertainty about things, okay? Because it's quite useful for game theory to be able to think about uncertainty in a kind of coherent way. But first, let's tidy up some little things from Chapter 5 and Chapter 6. The first is, all of the games we've looked at in the simultaneous games have been, 2 strategies, 3 strategies, up to 5 strategies in that coordinated effort game. But what about if you had sort of continuous strategies? The idea of continuous strategies would be, suppose it's a level of expenditure, okay, or a number like a price. So you've got 2 firms competing, and they each have to choose a price. Well, it's not just going to be, $1, $2, whatever. There's a whole range. And we'll see that the methods work the same way. In the text in Chapter 5, there's a lot of tough problems, continuous strategies. You don't have to worry about them, okay? If you just kind of look at the graphs and get the general idea of what continuous strategies are about, that'll be fine. Then a second idea we want to look at is sometimes Nash equilibrium ideas don't seem so sensible. Okay? And there's 2 situations, kind of thinking about risk, where they might not seem sensible, so I want to look at those. And then we'll come back, we'll start in these 2 bigger topics which interrelate sequential and simultaneous games. So, what I've done here is I've drawn a little box which, if you wanted to, you could think of as like a payoff table. Okay, and on the lower axis, the blue axis, you could put the level of advertising expenditure of a firm. And let's think of tobacco companies, okay? And or you could think of Coke and Pepsi, basically, okay? Coke could be a blue player, Pepsi could be a red player. You'd have one cigarette company be the blue player, one cigarette company be the red player. The idea is that people advertise in order to make profits and to get higher market share. So if we think of not just one strategy, but a whole range of strategies, we can plot them along a line. Okay? And then, similarly with the red players, we can think of a whole range of strategies and plot them along a line. Now, let's just pick arbitrarily one level of advertising expenditure, okay? Just some number. But I've got it here to the left, so it's a small number, okay? Not too large. And then I'm thinking, okay, I'm a company, I see this other company, well, I don't see anything, it's a simultaneous game. I'm thinking about what to do if they advertise just a little bit. So, if they just advertise a little bit, then maybe I want to advertise quite a bit because I could get a larger market share than they. But I don't want to keep on advertising, going way up here because that's just sort of spending money. The market is never going to be that big. And there's some best response. So the red dot idea, when I read up, I'm sort of thinking, well, if blue spends this much money, as a red player, what's my best response? Now, the best response will be, for a firm, might be in terms of profits, okay? So we're thinking, this red dot just tells us the best response of the red player. We could sort of conceptually do that for every level of expenditure, every level of advertising expenditure, and that's what I've done here with our little open circles that we had before. When we had a payoff table, or a payoff matrix, I was using these little red circles to find the best response of the red player to whatever the column player was doing. Well, here the red player is row. Row is they're going to choose a level of expenditure. Blue player is equivalent to the column, and I'm just plotting some possible best responses. Okay. Now, generally, these curves could go in any kind of direction depending on the nature of the game that you're looking at. But here you might think, look at if the blue guy is advertising heaps, then for the red guy, it's not going to pay much to advertise very much, because this other guy's doing so much advertising. Profitability of advertising for you is really small. Okay, but when he's advertising a small amount, we'll want to advertise more. Okay, so that's the kind of concept behind this particular curve. So you got that idea, or these dots? But I could join all those points together in a line, and then I wouldn't just have for any one particular level of expenditure, or advertising expenditure for blue, I'd have a best response curve for every level of expenditure. And that's what we mean by the continuous strategies, okay? The strategies for the red player are their level of expenditures. What's their best response strategy? Well, that'll be the most profitable one if I think about what the other guy's going to be doing. Well, the other guy could be doing a little bit of advertising, a moderate bit, or a lot. Those are my best responses, okay, along that curve. Now, I put these little arrows up here because the idea is that I haven't put the payoffs in this matrix. And the reason you don't is that it would just be full of numbers, which would be the profit levels for the blue player and the red player if you knew what the profitability of these various activities were. Okay. But generally the idea is that profits will be increasing for the red player moving in this direction, and profits will be increasing in this direction moving for the red player. And that's just kind of like their highest profit level. It doesn't tell you what that payoff level is. So this strategy space is a little different than the payoff matrix because we're not putting payoffs in there. We're just kind of plotting the combinations of best responses for each of the players. Now, I could do the same thing for the blue player. Remember the little crosses we had when I put the noughts and crosses in the payoff matrix? I said, well, supposing the red player puts a certain level of advertising expenditure out, then the column player would find their best response. Well, supposing that X is the best response to a particular level of advertising expenditure for the red guy about there. Or when the red guy's advertising a lot, the blue guy doesn't find it very profitable to advertise very much. But when the blue guy is the red guy is advertising just a small bit, the blue guy finds it profitable to advertise. Okay. So we get a best response curve for the blue player. Join all those points up, or if you can do the calculus and things in the text, if you knew the profit functions, you could actually go ahead and calculate these things. But generally, those are just like we had in the payoff matrices, okay? And if you look at the intersection of those two curves, so that's where, for the intersection is a point where there's both a red circle and a cross. So there's noughts and crosses together. That's our Nash equilibrium idea. Okay? And the Nash equilibrium idea in this advertising game would be specification of an advertising level or prediction of the advertising level for the red player and the advertising level for the blue player, such that each player is making a best response to the other guy in that particular specification of strategies. Okay? So each of them is predicting appropriately the level of advertising expenditure the other guy is doing, and then looking at their own calculations and thinking, what's the most profitable thing for me to do? Okay? So if the blue player does S star, the red player will do his red S star as his best response. If the red player plays S star, then the blue player will do blue S star as his best response. And a little square, it's just like in the payoff matrix, the noughts and crosses, one Nash equilibrium. Now what's interesting about these kind of games is that when you have the continuous strategies then, you're looking for an intersection of curves rather than the plot of noughts and crosses or simultaneous best responses in a payoff table. But you often get this phenomena that, just like with like in a pricing game or in an advertising game, Coke and Pepsi spend a lot of money on advertising. And the reason that Coke spends a lot of money on advertising is because Pepsi's spending a lot of money. And the reason that Pepsi's spending a lot of money on advertising is Coke's spending a lot of money on advertising. And all that money on advertising, if they could just sort of cut back both at the same time, it'd be better for both of them, right? So it's kind of like a prisoner's dilemma. And the same way with the tobacco companies. When in the 60s and 50s, 60s, 70s, tobacco companies would spend heaps of money competing with one another to get customers, okay? And the idea was all of this expenditure is probably pretty wasteful. And the only reason they do it is it's sort of a strategic thing. You know, the other guy's doing a bunch of advertising. If I don't do any advertising, then I'm not going to get any business. So I figure out what my best response is. They figure out what their best response is. We come to this equilibrium level of advertising that could be pretty high, right? If we could all just cut back our advertising level, we could all be much better off. So how did they cut back their advertising level? Well, this is a little cynical view of the restrictions on smoking, but it became very, very profitable for when they put on these health warnings and on cigarette packs, and they got because the companies then were able to uniformly reduce their level of advertising, and they made a lot more profits. Okay? Because otherwise they weren't able to get coordinated. It's like Coke and Pepsi can't get coordinated to reduce their level of advertising because they don't have someone who's coming in, well, not yet. We'll have the health officials pretty soon saying, Coke, you cannot advertise it. Pepsi, you cannot advertise it. They'll be sitting there. Ah, yes, finally. We've got a way of coordinating ourselves to make more money, okay? Because we're spending all this money. So again, you could think of that as it's like a prisoner's dilemma, and you use the continuous advertising or the continuous strategies based to analyze those kind of games. You need a bit of mathematics to do this kind of properly in the sense of figure out what rational, intelligent players would do in the game. Okay. So we're going to forget about that. I just want to introduce you to that idea of continuous strategies. Same basic fundamental concepts that we had before. Now, let's go back to our payoff matrices and look at this idea of a Nash equilibrium a little more closely. Okay. When you leave this course, you want to be able to remember a few things, and one is the idea of a Nash equilibrium. So someone asks you, what is a Nash equilibrium? You think, oh, God, I can't even remember from 2, 2, 3. What would that be? Well, strategies are a way of behaving, right, in all the circumstances you can find yourself in. So what you're trying to do is say, well, a Nash equilibrium is a strategy for each of the players in the game. So that's one thing, it's a strategy for each player. So it's kind of a list of strategies. And even when people all expect those strategies to happen, and they work out, given what I expect other people to do, am I doing the best thing for myself? Okay, a mutual best response is a Nash equilibrium. So that's the idea of a Nash equilibrium. Now, if we look at this simple payoff matrix that comes from our text, let's kind of walk through it, okay? Just do the best response analysis that we had before. We do our best responses for the red player. If the column player does A, then 2s are better than 1, so we put a little naught. Remember, there's 2 best responses here. If the column player does A, either T or B will get the red player 2. If the column player does B, then 3 is the best response, because 3 is better than 2 and 2. Okay, so T is the best response. It gives a higher payoff. Same way, if the column player does C, then 3 is the best response. M is the best response with a payoff of 3. Okay. So those are the best responses for the red player. And let's look at the best responses for the blue player. Well, given the red player does T, we get a 2 and a 2. Given the red player does M, 3 beats 2 and 2, so we put a little X there, ditto here. So those are the pattern of best responses, and there's one cell up here, which is the Nash equilibrium, right? T and A are what the theory would predict would happen in this game. And the reason that we predict this, that we'd say, given the strategy, red strategy T, if A expects that to if blue expects that to happen, A is his best response to that strategy. And the red player expecting A, T will be his best response, okay? So what, from the perspective of the red player, is his best response, is also, from the perspective of the blue player, what he expects red to be doing, and vice versa. Okay, so there's a consistency, a logic to that Nash equilibria. They're mutual best responses. And so the rational intelligent player would say, this is what we'll do. But when people have played this little game, often that's not the pattern that emerges. And what emerges is this bottom row. Look at the bottom row from the red player's perspective. If you play B as the red player, you're going to get 2, or 2, or 2. You get a guaranteed 2. So let's just highlight those ones. If you play C as a blue player, you're going to get 2, 2, 2. So this combination down here, this combination of strategies, B and C, has the same payoffs as the Nash equilibrium, but it's safer, okay? Because it's safer for each player, because in the Nash equilibrium, if the red player plays T, there's a chance he'll get 1. If the blue player plays A, there's a chance that he will get 0. Okay? Sorry, say it again. I think I did that one wrong. If the red player plays T, there's a chance that he'll get 0. Yeah, I pulled out the blue there. I read it the wrong way. Okay? Say it again. If the red player plays T, there's a chance that he's going to get a payoff of 0. If the other guy plays C. And why would the other guy play C? Well, the other guy might play C because it's a very safe strategy for him, and he can get just as much as he could in the Nash equilibrium. Vice versa, if the blue player plays A, then he runs a risk of getting 0. Why would he get 0? Well, because the other guy might be playing B, who's going to guarantee himself 2, which is just what he can get in the Nash equilibrium. So this is kind of a play it safe strategy. So this is the kind of reasoning that, you'll often meet. I mean, we've had all kinds of strange things happen in class where people, not strange, they're interesting empirical outcomes. It's the way people reason, okay? Now, there's a way of reasoning from the theory standpoint that says people don't just play it safe. Right? In Nash equilibria, people play their best responses. And so the way that you sort of, as a theorist, as a game theorist, you'd say, okay, well, I see your argument, okay? If the payoffs here are the same as the payoffs there. The strategy B is safer than the strategy T. In particular, for both players, it's safer because each of them is going to get a guaranteed level of 2, no matter even if the other guy makes a mistake. Okay? But the problem with expecting that to happen is that you're basically expecting people to act in an irrational way. For example, if I'm the red player and I'm sitting there, the blue guy expects me to play B, and I expect him to play C. Should I keep playing B? Well, if he's playing C on the expectation that I'm going to play B, then he's going to be wrong in the sense that if I switch from B up to M, I can get a higher payoff of 3. Okay? So if he expects me to play B, he's expecting me to do something irrational that's against my best interest. You're saying, well, isn't it safe for you to play B? Because B gives you a 2 no matter what the other guy does. That's true, it does. But I expect the other guy to play C. If I believe the other guy is going to play C, what's my best response? Well, it's to play M. Okay? And then the other guy should be able to figure that out too. So if he plays C, he should be expecting me to play M. And if he expects me to play M and not B like he initially expected, then he shouldn't be playing C anymore. He should be playing A. And then if he's going to play A, I should be playing T. I could play B, but if I play B and he expects me to play B, then he will be playing B over here. And if he plays B over there, then I should play B up here, in which case he should be playing A. Okay? So the idea is that this pair of strategies can't survive that kind of thinking about best response analysis. Okay, now it's true, if the only objectives were people to play safe, okay, then these wouldn't be the payoffs in the payoff matrix. But in this game, that combination B and C, though it looks like it's reasonable, doesn't pass that test of surviving a kind of a best response criticism. Are people doing irrational things given what everybody else expects everybody else to believe? Well, if everybody's believing C and B, then they aren't doing rational things. Okay, red player can do better by playing M. Blue player could do better by playing B. Both of them can do better given what they believe, which is supposed to be C and B. And it's only this Nash equilibrium which can survive that kind of analysis, that the other person really is playing a best response to what he expects to happen, or each of the players is. Okay? So when you're looking at the concept of Nash equilibrium, I mean, it's quite possible in real life situations people will play it safe. Okay? But we're thinking, okay, that's true, but as people get more experience and they learn if this is the nature of the game, and these were the actual payoffs, notice that's a bunch of ifs all the way around, then you'd sort of think about it and you'd think, well, now I would expect, T and A to happen, because otherwise anything else in that payoff matrix would involve somebody doing something irrational. And as long as they're kind of taking it seriously enough to think about what's the rational line of play, they shouldn't expect anything else to happen. Now this argument is attributed to Roger Myerson, when people say, well, why would you expect a Nash equilibrium? And his answer is, well, why not? Okay. And the idea is, okay, we're predicting a Nash equilibrium here. Tell me something else. What else would you think would happen? Well, if the play it safe option looks good, and everybody expects it to look good, then they'll be doing irrational things on the basis of their expectations if that actually happens. Okay, so the why not kind of argument is a useful way to try to defend the Nash equilibrium idea. Now, notice that there's a lot of assumptions about the Nash equilibrium. You got this rationality, you got this intelligence, you got this willingness of people to actually kind of think things through, which we saw in class didn't happen all the time. Okay, but the theory says, look, in some cases where the stakes are high enough, people are going to be taking this thing seriously and working out what the what mutual best responses are. So that's one idea about the Nash equilibrium. There's another idea which has been used to criticize the Nash equilibrium concept. You haven't got this payoff matrix on your handout. It's just a simple 2x2 game. The idea here isn't so much play it safe inside the game, but what if you got the game wrong? Okay? What if the other guy makes a little mistake? Okay? Those two questions. What if I'm playing the wrong game, which is often in real life is a difficulty because you don't know what games you are playing. And that's where the uncertainty comes in, which we want to be able to think about is, well, I don't really know exactly, if I'm playing a game with Jason, I really know what his payoffs are. Okay? And I don't really know whether he's really very rational. He might make a mistake. He just, it's a bad day, doesn't really see things clearly today, pushes the wrong button on a lever or whatever they're doing. Well, let's look at this sort of simple, it's a very simple game to get across the point. So the blue player has two choices, left or right, and the red player can choose up or down. And from the blue player's standpoint, these numbers, 9.9 to 10, 9.9 to 10, they're supposed to be close. Okay, now we already said, you always ask what the numbers mean. Well, here, think of them as dollar payoffs, okay? Or something where the magnitudes do matter. There's not much in it for the blue player playing left to right. Right? It's true that, left is a dominant strategy because 10 is bigger than 9.9, 10 is bigger than 9.9. And given that dominant strategy, the red player should think, well, 10 is better than 9. But if by chance, or some mistake, or we're in the wrong game, the blue player plays right, and the red player plays down, he's getting a big loss. Okay? So in this kind of game, it's true the Nash equilibria here is down and left, but if you were playing this game and people are playing it for money, the red player probably going to play it safe by playing up, because at least he can get 9 or 8. Sorry, this should be a red 8, not a blue 8. Okay. And I mean, the reason is you want to avoid this other problem, which is I might not be, the other guy might not be as rational as I think they are, in which case, if I play down, I'm going to get a disastrous outcome. So that would make it sensible to play safe. Okay? Now, what we'll see is when we model and think about the idea of uncertainty in a game, where you sort of think, well, what are the chances of the blue player playing to the right-hand side? Just supposing he had a little chance of making a mistake. Okay, that would be a different game. And than this, we haven't learned how to analyze that game yet, but we do. We'll see the Nash equilibrium works perfectly well. The most sensible thing in the world to do, given any reasonable probability the guy is going to make a mistake, is to play up. But in this game by itself, just looking at this game here, if we know the payoffs exactly, there's a big if. If we know this payoff exactly, then the Nash equilibrium is a reasonable thing to do. Why we don't think it makes sense is that this might not be the exact game. Okay, there might be a game where blue's payoffs aren't like this. He wakes up one morning and he confuses the 9.9 into 10 and he flips the other way. Okay, or we got the payoffs wrong. So just keep that idea in mind that this is a criticism of the Nash equilibrium. But really it's a criticism of a too simple model, a too simple way of thinking about it, as if there were only two strategies, and we haven't figured in here, what if this isn't the game you're playing? What if blue actually, when he plays right, wakes up one morning and has a 10.1 over here? Okay? What if those are his payoffs? He's got something better to do on that day. Okay? Well, we're going to see a way of analyzing those kind of games, and in that game, the Nash equilibrium would do the sensible thing, which is say, if there's any chance of that, I'm going to play up. Now we come to the little hard part in the in today's lecture, because this is going to force you to connect simultaneous game reasoning with sequential game reasoning. Okay? And what I've done is I've put up a sequential game, which was a game where the monetary authorities were playing against the fiscal authorities, or we call it the Reserve Bank and Parliament. And the idea is, the red player could either run a budget balance or budget deficit, and the monetary authorities could have low interest rates or high interest rates. Now, when we're looking at this kind of game, sometimes, when you see the structure of a game, it's a good idea just to have a look at a simultaneous version of the game. Okay. Now, this simultaneous table of payoffs is not the sequential game. The sequential game says the red player moves first, then the blue player gets to observe what the red player has done and move. Whereas if we look at the simultaneous version of this game is saying neither player can observe what the other player can do. But if you look at this particular game here, you'll see 4 beats a 3, 2 beats a 1. So the red player has a dominant strategy. What about the blue player? 4 beats a 3, 2 beats a 1. The blue player doesn't have a dominant strategy. But the blue player can anticipate the red player's dominant strategy and then play the strategy on the right-hand side. So this would be the Nash Equilibrium. Say that again. And if we were analyzing this as a simultaneous game, one of the players would have a dominant strategy. The other player, anticipating that, would choose to the right. And notice they both forgo some nice jointly better outcomes here to the left. This isn't a prisoner's dilemma, because the prisoner's dilemma has a property that every player has a dominant strategy, but it is like the prisoner's dilemma in that the equilibrium gets them somewhere which is bad compared to if they didn't play their equilibrium outcomes. Now, so this is a game where this simultaneous game is a game where each player has a dominant strategy. But this is not the sequential game. Now what I want to do is analyze this sequential game as if it were a simultaneous game. Well, isn't that how we look at it? And the answer is no, because this simultaneous game assumes a particular information structure, right? It says the blue player cannot observe what the red player is doing. The red player cannot observe what the blue player is doing. Whereas this game here, the information structure is one of them can observe what the other is doing. So how do we analyze that as a simultaneous game? Well, what I've put down below is a payoff table. Okay? But a payoff table is 2 by 4. Why is it 2 by 4? Well, the red player has two things they can do. BB or BD, budget balance or budget deficit. But the blue player has 4 possible strategies. Because remember, a strategy is a complete specification of what you can do in all the circumstances you find yourself in. Right? So for the blue player could play low and low. So we should put that right there. The blue player can play low, high. So it's the next strategy. The blue player can play high and low, which is the strategy here, high and low. Or the blue player can play high, which is that strategy over there. Okay, so along this top row, we specify the strategies. Now, remember, the strategies are a complete specification of what you do in all the circumstances you find yourself in. Now, the strategies, so when we're in a simultaneous game, are supposed to be, oh, the blue player can't see what the red player is doing, and the red player can't see what the blue player is doing. It's true. And we're just thinking about their strategies. But the strategy for the blue player has kind of embedded in it, what would I do if I saw the red player do this? What would I do if I saw the red player do that? Okay, so these strategies, they do have kind of a component of observability built into them. Right? Now let's match the strategies up, like we do with the payoff table, and figure out what the payoffs will be. So supposing the blue player always plays low. He plays low up here, and he plays low up there. And the red player plays BB. Well, then we match BB with low and low, and what's going to happen? We're going to get a payoff of 3 and 4. So this number here, the 3 and 4, plotted down right there. What about if we play BB against L and H? What's L and H? Well, low in the top, high in the bottom. Well, BB matched against low in the top, high in the bottom is still going to be B, low. Why? Well, we'll get our 3 and 4. We'll plot it down over here. Now notice the payoffs are the same. The only thing that's changing between these two strategies is what the blue player is doing down here at node B2, and he's never going to get to node B2 if those are the matching up of the pair of strategies, because the red player is playing up here, leading to node B1. Okay. Just keep plowing through. Where do these numbers come from? 1 and 3 and 1 and 3. Well, if you play, the red player plays BB, the top row, and the blue player plays the strategy high up here, low down there, then match the red BB against the high, and we'll get 1 and 3. Take that number, plot it down there. Similarly, if the blue player always plays high, high, and high, that's the strategy. You match it up with the red player who plays BB, then by playing budget balance, taking it up to node B1, the blue player always plays high, off 1 and 3, which is what we get there. Again, you ask, well, why are the numbers the same here? Well, the only difference between these two strategies is what the blue player is doing at node B2, playing low or playing high. But if the red player plays BB, we're never getting to node B2. So though the player's strategy varies, the payoffs don't vary, because in this row, we're never going to get to B2. We're always going along node. So the action BB leads to node B1. Okay. Just to be pedantic, let's keep going on a bottom bit. Okay. Supposing the red player plays a budget deficit, so we play the lower action. The blue player is playing low all the time, so he's playing low here. Well, low at the top is going to be irrelevant, given that the red player is playing BB down this way here. So the payoff is 4 and 1. We take this number, plonk it down into that cell. Let's do the second one. BD against the strategy low at the top, high at the bottom. Well, low at the top, high at the bottom, match that up with BD, that's going to be a payoff of 2 and 2. Because what the player does up here doesn't matter. When they match those two strategies together, we're going to get the payoff 2 and 2. So we go down, put it down here. And similarly with these last two numbers, okay? So it takes a little while to get your head around this concept, but you're just trying to build up the payoff matrix for a game which you could think of as a simultaneous game that really embeds all of the strategies that the blue player can have. And we get this pattern of payoffs. So what? Well, let's have a look at it. Now we can analyze these two games. Let's go back and analyze the sequential game. If we use rollback reasoning to analyze that game, what's going to happen? Go to node B1. We see a 4 is bigger than a 3. We prune that branch there, and we expect the blue player to play low. Go to this node here. A 2 is bigger than a 1. We prune this branch, and we expect the blue player to play high. The red player, we don't expect to play BD, because if he plays BD, he's going to get a 2. If he plays BB, he can expect to get a 3. 3 is better than 2, so we prune that branch. And we would expect, if you like, the path of play in the rollback equilibrium to lead us out this way here, 3 and 4. And we would expect the strategies in the rollback equilibrium are for the other guy, if he got to node B2, to play high. Now that rollback equilibrium turns out to be the combination of strategies low up here at B1, high down there at B2, so it's this column, and this row. So that's the rollback equilibrium. Let's pull that out of there for a second. Now analyze the payoff matrix itself, see what we get. Well, best responses for the red player are 4 is better than 3, 3 is better than 2, 4 is better than 1, 2 is better than 1. So we put in these best responses. Do the same for the blue player. 4 is better than 3, 4 is better than 3. There's 2 best responses, so we just mechanically crunch out our little x's. 2 is better than 1, is better than 1, 2 is the same as 2, so we crunch out our little x's. And what do we have? 2 Nash equilibria. There are 2 Nash equilibria when we look at the game from a simultaneous perspective. But there's only 1 Nash equilibria when we look at it from the rollback perspective. With an idea? Okay, now, just as an exercise, we did this entry deterrence game to death when we looked at this. We looked at sequential games, and what I'd like you to do is take that entry deterrence game and analyze it as if it were a simultaneous game. Go ahead and plot the 2x4 simultaneous game matrix and see how many Nash equilibria there are in that entry deterrence game. Okay. And there's two. How could there be two Nash equilibria when we look at the game from one perspective, but there's only one kind of sensible rollback equilibria when we look at it from another perspective? Okay, so that's the question. That's what we want to answer. We want to relate these two concepts. With me so far? Jason, you hanging in there with the idea? Anyone got any questions about this sort of multiplicity of the equilibria? Once you're kind of looking at the payoff matrices, it's kind of mechanical. You sort of think, well, I'm just going through it. I'm finding two Nash equilibria. What are these two Nash equilibria? Well, I'm going to pull out this other Nash equilibria, which is a combination of always playing high and playing a budget deficit, which got us into this low payoff equilibrium, and have a look at it. Okay, so let me block out the left-hand side. What I did up here in the top graph is highlight the strategies of the red player to play BD, and the strategy of the blue player, which is always to play high. Now, what that's doing is that when we match up that strategy of the red player with that strategy of the blue player, we're coming up with a payoff 2 and 2. But implicit in that payoff, implicit in the strategy of always playing high is to have the blue player up here at this node doing something that's irrational. Why? Because if you look at it from the... I put this little box around here. We're going to call this a subgame. Okay? Now, the idea of a subgame when you have a sequential game is, basically any part of a game tree which if you kind of pulled it out on its own would form another game. Okay? So you look at that subgame, and here there's only one player in that subgame, the blue player, but the blue player is choosing high, which is a payoff of 3, compared to what he could get if he chose low. Okay? So he's doing something irrational at this point, in the sense that the strategy specification says, okay, if I get to node B1, I go high, and if I get to node B2, I would go high. But then you'd ask, well, why would I ever expect the blue player to do that? I mean, it's a Nash equilibrium in the sense that given that he's going to play high and high, the red player is better playing BD, the lower row, than the top row, because 2 is better than 1. Okay, and given that the row player is playing BD, then either HH or LH would be a best response by the blue player. So this is a mutual best response. It is a pattern of strategies which people could believe, and if they did believe them, each of them would be playing a mutual best response in them. So it's a Nash equilibrium. But it's not a very sensible Nash equilibrium. Okay? Now this is the first time that we've sort of said, hey, wait a second, there might be something a little bit dodgy about the Nash equilibrium concept. Okay? When we look at a simultaneous game like this, if the simultaneous game is representing kind of a pattern of play, lots of different strategies that players might do, you might think, well, is that it? Are those sensible strategies? And it turns out that no. If you look behind that strategy H and H, it's not very sensible for the blue player to be playing high up here. They're doing something irrational. So embedded in that concept of Nash equilibrium right here is an idea of non-rational play. So we have a new name for this kind of equilibrium. Let me just put these two guys back up here. When we look at the equilibrium on our left, which was the one that gave the payoffs 3 and 4, let me think, I had the rollback equilibrium specified out there like that, okay? If we look at the subgames in that equilibria, like if we go down to this game down here, notice that the blue player is doing a sensible thing. 2 is better than 1, okay? But in this particular game, there's a sub-game where the blue player is doing something not sensible, irrational. Okay? Now, in both of these equilibrium concepts, the sub-game is not on the path of play. That is, we're going out here, we expect this to happen, or in this one here, we expect this to happen, and these two sub-games are off the path of play. We don't expect them to happen, right? But one of these equilibria, Nash equilibria, this one here, seems a bit more reasonable than this one here, on this grounds that there's an element of irrational play here. Now, when we reach chapter 10, we talk about manipulating strategic games, we're going to come up with an idea of credibility. Okay? And the credibility idea is that I make a promise, I make a threat. You're sitting there thinking, should I believe that promise? Should I believe that threat? And then you use the best response analysis and you'd sort of say, ooh, okay, I believe that threat because I can see that it's in his interest to carry that out. Or I believe that promise because I can see it's in his interest to carry it out. Or I don't believe that threat because he's never going to carry it out, it's against his interests. Or I don't believe that promise because it's not his interest to carry it out. Okay, so we use that best response reasoning to believe threats or not. Well, one way if you look at this right-hand matrix, you can sort of think of the blue player embedded in this strategy is kind of like a threat. Okay? I mean, in this particular game, we can't see why the blue player would want to play it because he's going to play this equilibrium rather than the other equilibrium because he's getting a worse outcome. But just take this concept by itself and you sort of think, well, what he's doing up here is something against his own interests. 3 is worse than 4, but he's hurting the other guy. Okay? So you can think of that. This strategy has embedded in it sort of a promise to hurt the other person. If you like, it's a threat. Okay? But it's not a believable threat. Now, there isn't any actual threat. There's no language. There's no communication in this game. But in the strategy, you can think of, well, if I'm always playing high, then implicitly what I'm doing is saying, well, look, if you play BB, I'm going to play high. I'm going to hurt you. I'm going to do something against my own interest to hurt you. And that would be called a non-credible threat. So the idea, when we come up with an equilibrium notion, we call it subgame perfect equilibrium or subgame perfect Nash equilibrium, is that we're saying if we can find, we may find Nash equilibria concept where in some subgame behind this payoff matrix, there's an element of rationality, then we throw it out. Okay? It is a Nash equilibrium. But it's only a Nash equilibria because there's some non-credible threats or promises in it. Okay. Let's leave this idea, and I want you to, for tomorrow, try the entry deterrence game. Do exactly the same analysis with the entry deterrence game to come up with the pattern of equilibria, and you will find more than one equilibria in the entry deterrence game. And then what you want to do is take that other equilibria that doesn't follow along the rollback path of play and ask, well, what is the irrational element in that equilibria? Because there will be one. Okay? This is the kind of thing where at first it seems, well, you know, why are we doing this? Well, we're doing this because we want to understand the concept of equilibrium play, best response play, rational intelligent play in a game. And what we've done is we went through a bunch of rollback equilibria, Nash equilibria, and we're really pushing this Nash equilibrium idea as a sensible way to play the game. But now we come across these examples where maybe Nash equilibrium isn't so sensible. And why isn't it so sensible? Because sometimes it will have embedded in it plays of a game that you don't expect to happen off the path of play where people do irrational things. And so the subgame perfect idea says, well, let's forget about those Nash equilibria. Let's just concentrate on the ones that are in a subgame. There's perfect rationality. That's the way to think of subgame perfect equilibrium. Now, I think that is, now it's this one more sophisticated concept that we're going to look at. It's called Bayesian equilibrium. We have some uncertainty here. But the concept is kind of interesting. Okay, we say equilibrium, strategies, mutual best responses. And then we think, ooh, some of those mutual best responses might involve irrational things along paths of play we don't expect to happen. Okay, so they're kind of embedded in those paths of play we don't expect to happen, or a bunch of beliefs about things which we don't expect people to lead people to. So we don't expect players to have beliefs about what other people do, where it embodies the notion of irrationality. So we eliminate those, and we deal with this idea of a subgame perfect equilibrium. Sorry, that was. This particular concept is a new idea for Nash equilibria. Okay, subgame perfect equilibria are Nash equilibria. The rollback equilibria captures that Nash equilibria, but the rollback captures more. It also says, if you're not on the path of play, you're down here at some other subgame, you can't expect people to do rational things. Okay? Whereas this equilibria down here says, well, if you're not in the path of play, somebody's expecting other players to do non-rational things, and we don't think people will have those kind of beliefs. At least that's part of the theory of rational intelligent play. Okay, let's have a quick look at analyzing a simultaneous game as a sequential game. Remember, what we just did was we took a sequential game and we analyzed it as a simultaneous game. We didn't change the information structure. We're just saying we had a 2x2 game and then we had a 2x4 payoff matrix, and we said we could analyze that either way. Well, look at the simultaneous game. This is our basic entry deterrence game. We have invest or not invest. Red player gets 2 or 1, 4 or 3 has the dominant strategy. The blue player can either enter or not enter, but the blue player doesn't have the dominant strategy. 3 is better than 1, but 4 is better than 2. Okay, and then we could work out that the equilibrium in this case is going to be with this cell here, where the blue player will enter and the red player will not invest. Okay. Let's just imagine a sequential game where the red player goes first. Now, actually, the red player doesn't go first, but we're going to see how to deal with that. Okay. So we put down our entry deterrence game that's like this. The red player invests. The blue player doesn't invest. The blue player can enter or not enter. Blue player can enter or not enter. But the problem with this game is that the blue player can observe what the red player is doing before they make their choice. Whereas in the simultaneous game, the whole idea is you can't observe that. Okay. So we introduce a new concept. We put a circle around those 2 little dots. Okay. And the circle is called an information set. It's actually misnamed because it really should be called a lack of information set. The idea is that when the blue player in a sequential game like this comes to make their move, they don't know whether they're at this node or they're at that node. There's uncertainty about which node they're at. Now, let me just remove this again. Without any uncertainty in the game, the blue player, when it's their turn to move, they're at node B1, they've seen that the red player invests, they can make a choice. They can make that choice depend on what the other guy does. Okay, if he invests, I can do something. If he doesn't invest, I can do something else. Because they can observe it. So their strategies are a little more complex. They're contingent. They can say, well, I can make it depend on what the other guy does. But in the game where there's an information set, if you can't see what the other guy's doing, you can't make your choice contingent or depend upon what the other guy does. And so, in a way, we only have 2 choices at that information set. Okay. Now, I kind of masked the payoff numbers in the back in this, because what I'm trying to get at here is that think of the information set as a big node. This is like one node. You're just not sure exactly where you are. So you have to choose, am I going to enter or am I going to not enter? Now, if I enter and the other guy invests, my payoffs are going to be up here at 1 and 1. But if he didn't invest and I entered, then my payoffs are going to be at 2 and 4. And the idea, there's uncertainty in your head about what the other guy is going to do, so you could end up, as a blue player, either getting 1 if the other guy invests, or getting 4 if the other guy doesn't. Just like here. Okay? Looking at this simultaneous game, if you choose to enter and he invests, you're going to get 1. If he doesn't invest, you're going to get 4. Okay. Similarly, if you decide not to enter, then if he invests, you'll move it along this path, you'll get the payoff 3 and 3. But if he doesn't invest and you've not entered, then you'll get 4 and 2. So that's exactly what we have down here in the payoff matrix. It's like, okay, if he invests and I don't enter, I'm going to get 3, says the blue player. But if he does invest, if he does invest and I enter, I'm going to get 2. So this way of this simultaneous game with an information set is one way of representing. Did I say that right? The sequential game with the information set is one way of representing simultaneous game as a sequential game. And that's a lot to take in here, because this is a sequential game with an information set. It represents this simultaneous game. Now, again, as a little exercise, I started out with my representation with the red player moving first and the blue player moving second, plonking in this information set. A little homework exercise: have the blue player start first, have the red player move second, put in your information set, and have a look at what game tree you get out of that. It'll be just as good a representation as a sequential game of this simultaneous game as the one that we've drawn up here. Okay, so 2 exercises for tomorrow. One is look at the entry deterrence game, analyze it as a sequential game, sorry, as a simultaneous game. And the other one is take this this simultaneous game, this 2x2 simple simultaneous game, and represent it as a sequential game with an information set. Again, tomorrow we'll come back to the information set concept. I've got a card game where it'll become a little bit clearer as we use this information set idea to represent uncertainty in a larger game tree.